eigenvalue greater than 1, do not use that rule. It's been criticized so often. It does have some theoretical foundation, but we use the parallel analysis to determine the number of factors, and it told us that we should extract 3, in my opinion, because I ignored the other 2 that were extremely small and probably just correlated residuals. Maximum iterations for convergence 25. It's quite rare to need more. I would say that if you do need more, if you need to pump that up, there's probably actually something wrong with your model. You're probably extracting too many factors, or there's some multicollinearity in your data. It's usually a problem, I think, if you need to change your convergence iterations. So click to continue. Rotation, as I explained in the principal components analysis, always choose a oblique rotation. So there's varimax, quadramax, equimax that are orthogonal, and then there's direct oblimin and promax that are oblique. And so what these will do will rotate the factors in such a way that the axes will not be at total 95-degree angles to each other, because they'll be allowed to correlate with each other. And in the real, in experience, in nature, most factors are correlated with each other to some degree. So it's unnatural to force them to be uncorrelated, as varimax forces them to, whereas direct oblimin and promax allow correlations. Delta 0, I'm not familiar with any research to show that using one delta value as your one value is better than the other. There might be some research out there. I'm not familiar with it. I use direct oblimin. It hasn't steered me wrong very much. I think a lot of this, a lot of use of orthogonal rotation exists because there was a time where getting computers to do oblique rotation was just tough, and so today, I think more and more people agree that using an oblique rotation is the best, because if your data are naturally uncorrelated, if the factors really are uncorrelated, and that's the best representation in terms of gaining simple structure, well, direct oblimin will produce an unrotated, basically unrotated, or I should say it'll be rotated, but it will be a orthogonal uncorrelated factor solution. So you get the best of both worlds by using direct oblimin. So display rotated solution. Loading plots, I don't get a lot out of loading plots myself, especially if you have anything more than 2 factors. It really starts to get complicated in my opinion. So I'm going to click on OK. Scores, I don't really want any scores. You can get scores for each factor that you can then use to correlate with other things, and I think that can be quite useful, but I'm not going to do it in this case. And then we got the options here. Coefficient display format, and I think that's important. You want to sort them by size. It really greatly facilitates the interpretation of the factor loadings, particularly in the pattern matrix. But then there's the suppress small coefficients, and a lot of people tick that, and I don't know why. I think you should see information. If you you'll see some factor loadings that are small, and I'd rather see that it's 0.29 rather than 0.05. So if you suppress small coefficients and you specify, a value of less than 0.2 or something like that, you're not going to really see what's exactly going on. So I never click on that. I think in this case, I actually want to see the factor loadings. I want more information. So we click OK to run the analysis, and the first table that we get in the factor analysis is the descriptives with the means and the standard deviations. I think it's always important to check out your means and standard deviations, because it can usually alert you to some errors in your data. I haven't actually looked in this demonstration to look for outliers and some data input errors. I'm going to assume that you've already done that in your data. You should do that for every analysis you do, not just factor analysis. But the item, I'll note that the items are all, roughly what I'd expect, somewhere in the 1 to 3 ballpark. Then we get the correlation matrix, and we can see that there are a lot of positive correlations amongst all the items. So there's going to be a global factor, there's going to be a general factor in my data, but there's also a little bit of negative. There's a little negative correlation here, and some of the correlations are pretty small. That's a negative 0.008, negative 0.01. But overall, there's a positive manifold, what people call a positive manifold in the data, as I expect. So you just want to look at your correlation matrix to see that everything's going